Hi guys, this is Module 14, Lecture Notes 28. We're going to pick up right where we left off in the unit on rates. Last time we talked, we were talking about the rate equation. And I wrote it here again for you. Last class we learned how to calculate the rate of a reaction. And remember, rate refers to the speed of the reaction. We said the rate is equal to the rate constant times the concentration of a reactant, we call it A, to the X, times the concentration of another reactant to the Y. Okay, and we were able to plug in values from actual trials to figure out the exact rate of some reactions. What we were actually doing is we were figuring out the rate of a reaction at any given moment in time. If we were to stop the reaction and take a snapshot of just the piece of it at a certain instant, that's what we were calculating. And so this is often referred to as the instantaneous rate. And I like to think of it right at a specific time. Okay, think of it just like a snapshot. So that's what we learned how to do in the previous lecture. Today we're going to add on to our thoughts about rates or speeds of reaction, but we're going to talk about them in a more general sense. And we're going to talk about how factors like concentration, and later on we'll talk about temperature, how those factors can affect the entire rate of the reaction over a given amount of time. Okay, so first let's look at concentration. It says the rate of a reaction slowly decreases over time as the concentration of the reactants gets smaller. And you can see that here from this graph. I think it's very visual. At the beginning of the reaction, you have a very high concentration of reactants. You just added them. There's lots of them in there. But as the reaction progresses throughout time, you actually have less reactants. You have less reactants bumping into each other. And so, of course, your rate of reaction is going to eventually slow down. So you might make a note here by saying there is less to react with. Okay, remember, thinking about this in terms of collisions is always really important. If my container was full of beads in the beginning, there's going to be lots of reactions happening. It's going to happen really fast. But as we get towards the end of this reaction, there's less to react with, so less collisions are going to happen. So we can write out here to the side that as the concentration goes down, the rate of reaction goes down as well. Okay. The other thing I want you to note from this graph is that the reactant concentration never actually reaches zero. You can see that it gets smaller and smaller and smaller, but it never actually touches the x-axis. Reactions never actually come to completion. They just get slower and slower and slower throughout time. Okay, so that's another important thing to note. Okay, so in terms of what you need to know from this piece here, you need to know how concentration affects the rate of reaction. As the concentration decreases, the rate of reaction decreases as well. Next, we're going to look at temperature. How does temperature affect the reaction rate? Well, I think you probably have an idea because we've talked about how temperature affects collisions. And remember, collisions affect the rate of reaction. So back to our beads, at a low temperature, they're barely bumping into each other. And as you increase the temperature, well, you get the idea. They go crazy, they bump into each other more, and of course, your rate of reaction goes up. Okay, so The way that these are related is the higher the temperature, the higher the rate of reaction. Increase temperature, you're going to increase your reaction rate. Okay? And so a couple things that you probably saw in your book, but the rate constant also increases with temperature. And so since that's part of our equation for calculating rate, when K goes up, well, the rate goes up as well. And then they noted that a general rule of thumb that for about every 10 degrees increase in temperature, the reaction rate doubles. So temperature has a huge effect on the rate of reaction. So this one you need to know is increasing. On the back side of your paper, we're going to talk about 4 factors that increase the rate of reaction. And you got to play with some of these during your lab last time, I'm pretty sure. So these 4 are things that you definitely need to memorize. Okay. We talked about that as temperature increases, the rate of reaction increases. Okay, because you have more collisions at a higher temperature. And then we just talked about concentration, because if you have more reactants in there, there's going to be more collisions, making a higher rate of reaction. And then surface area. The greater the surface area, the higher the rate of reaction. And I think you were able to explore this with a whole tablet reacting versus a crushed up tablet. And you should see that when there's more surface or more pieces in there, the reactants are able to touch more often, making more collisions, therefore a higher reaction. So you see it really comes back to collisions when we're talking about most of this stuff. The last one that you need to know is probably a new word. It's called a catalyst. Okay, and I've defined it here for you. A catalyst is just a chemical that increases the rate of reaction. One thing that you should note about catalysts is they're not actually part of the reaction. They are not a reactant, they're not a product, they're not actually part of the chemical formulas of things that are reacting together. They're kind of just like bystanders. They're watching the reaction happen and they are not used up. They just speed up the reaction. Okay, so let's look down here at this graph at why catalysts speed up the rate of reaction. Okay, so this graph below is showing you a reaction without a catalyst. I'd like you to make that one color. It'll be this top line. Okay, so uncatalyzed reaction. There's no catalyst used in this top reaction. Remember, we talked about that often when you add reactants together, in order for them to become products, there's an activation energy barrier, and you have to overcome that activation energy. And in this case, that activation energy is quite large. In order to get over the hump from reactants to products, we need quite a bit of energy added, okay? Well, catalysts can help that out quite a bit. In the second line, this is a reaction pathway with a catalyst, a catalyzed reaction pathway. And you can see that it lowers the activation energy. This activation energy barrier is quite a bit less. And so catalyzed reactions happen much quicker. When you add a catalyst, it speeds up the rate of reaction because we don't need as much energy to get from here to there. So I'd like you to fill in that catalysts lower the activation energy needed to get the reaction started. Okay? You should be able to reproduce a drawing similar to this. You should be able to show that an uncatalyzed reaction has a much greater activation energy than a catalyzed reaction. So you might want to write yourself a note to study this. Okay. Lastly, at the bottom in this blank space, I want to show you how to write a reaction that includes a catalyst. And you're going to get a chance to do an activity with a catalyst during your lab time in class this week. Okay, you're going to be starting with H2O2, which is the formula for hydrogen peroxide. You know, like the stuff you put on cuts to clean them out. Okay. Hydrogen peroxide doesn't last very long under your sink. It slowly, over time, decomposes into just water and oxygen gas. Okay, so it'll last for a while, but if you haven't had a cut or a boo-boo in a year, it probably isn't going to be very fizzy the next time you come back to it, because it eventually will decompose. Well, we don't have that long to wait in class to watch peroxide break down into water and oxygen gas. We want it to happen right away before your eyes. So you're going to be adding a catalyst, and your catalyst is going to be yeast. Often the catalyst is just written right over the arrow in the reaction, because remember, it's not a reactant and it's not a product and it's not actually used up. So you can just put the catalyst right here. Okay, you'll probably want to make sure this reaction is balanced when you do it in class this week. It is not balanced right now, but that would probably be good practice for you to have that balance coming into class this week. So anyways, I hope you guys have a lot of fun with the activity, and I will see you guys for next lecture.